Okay, so we are doing the other part of 14.1 today. So we're going to start off talking about a little bit of an extension for molecular geometry, so the shapes of the molecules. In the SL level, we only went up to 4 electron domains because everybody followed the octet rule. So if you're following the octet rule, the most you can have is 8 electrons or 4 pairs, which means the most you can have is 4 bonds. But there are some elements that actually defy the octet law and have what we call expanded octets. So they can expand beyond 4 electron domains, and they can do 5 or 6. Okay, so I'm going to talk about the ones that have 5 electron domains first, and then we'll talk about some of the examples of the ones that have 6 electron domains. There's just a lot of information on here, so what you need to pay attention to is the number of electron domains. So this first column tells you the electron domain geometry. So if you notice as I go down here, like the next section, there are still 5 electron domains, so it's still considered trigonal bipyramidal for the electron domain geometry. What changes as you go through some of these are the molecular geometry, because the molecular geometry depends on both the total electron domains, but it depends on how many of them are bonding domains and how many of them are non-bonding or lone pair domains. And so if we compare these first 2 sections that are on here, you can see that both of them have 5 electron domains. So both of them are considered trigonal bipyramidal for the electron domain geometry. What is different about them is the number of bonding domains. So this one, all of the domains are all bonding. None of them are non-bonding. So there are no lone pairs in this third column. It's 0 right here. The other one down here, there's only 4 bonding domains. So the 5th domain is a non-bonding domain. It's a 1 right here. So it still adds up to a total of 5 domains. So that's why they're both trigonal bipyramidal in the 4th column. But because the first one, all 5 of the domains are bonding, the molecular geometry is the same as the electron domain geometry. So if you have no non-bonding domains, if all of your domains are all bonding, the 4th and 5th columns, the electron domain geometry and the molecular geometry, they're going to be the same. Okay. When you start having some of the electron domains be non-bonding, meaning you're going to have a lone pair or more than one lone pair on the central atom, that's when the molecular geometry changes, because you can, if you look down here at this one, it's called seesaw. It's not called trigonal bipyramidal anymore for the molecular geometry. So those are going to be different. Okay. And then the bond angles are also going to be slightly different. So I'm going to show you, you guys can see on the camera. So this is an example of the trigonal bipyramidal. So I can count. There's 1, 2, 3, 4, 5 electron domains, and they're all bonds. Okay. So it's trigonal bipyramidal because if I were to take, like some paper or something and actually create, like fill in the spaces and make, like a geometric shape with this, it would look like I have a pyramid up here that has a triangular base, because this is 3 sides here. And then on the bottom, it's like there's another pyramid. So there's like this is like the top of one pyramid, and this is the top of the other pyramid, and they meet here. Their bases meet here in the middle where you have these 3 that are connected. So it's trigonal bipyramidal because it's like there's 2 pyramids with a triangular base that meet each other in the middle. Okay. So all of the bond angles on here, the reason there's 2 bond angles listed in the notes is because when you have things that have 5 and 6 electron domains, you have what we call axial and you have equatorial bonds or bond angles. So if you think of like back to like geography, equatorial sounds like equator. So the equatorial ones are the ones that are going around the center. So this one, and this one. These 3 are the equatorial bonds. Axial is kind of like axis. So if you think of like the Earth's axis, like it goes from top to bottom, from like North Pole to South Pole. So this and this, these are the axial bonds. And so when you're talking about bond angles, if I'm talking about the angle between an axial and an equatorial, like right here, that's 90 degrees. I can see it looks like a right angle right here. But if I flip it this way, and if I talk about the angle between 2 equatorial atoms, This is more than 90. This is 120. And so that's why there are two different bond angles listed, because depending on which bonds we're talking about, the angle is going to be slightly different. So what you kind of need to know is that the 90 is axial equatorial. The 120 is equatorial equatorial, okay? This one is the other one, the seesaw. So I can see those, so there's still 5 electron domains. So I can see there's 4 kind of green atoms here. The purple is my central atom. But then there's this little thing here that I attached, which really, this is just to show you guys visually that there's a lone pair of electrons sitting up here. I can take it off, and then here's what it really looks like without that visual to kind of show you that lone pair is sitting up there. And so the reason it's called seesaw is because if I, put it on a flat surface, it looks like a seesaw. I can kind of make it go, it's hard to do on my hand, but you go down, up, down, up. So it's like a seesaw, like that you would see on a playground. And so if I set this down flat, I can go like this, I can go like this. And so it's like a seesaw. And so that's why the molecular geometry is called seesaw, since it has 4 bonding domains. And then this one other domain that's kind of sitting up here on top is non-bonding. It's a lone pair. On this one, if I look, the axial, so it's, even though I'm kind of showing it to you guys like this, like a seesaw, actually it was one of the equatorials is what was replaced. Because if I compare, these two, I can see they're similar in shape. The only difference is one of these white ones on the side was replaced by this lone pair, okay? But like I can turn them this way and you can see how I can see, the bond angles look similar. And so I still have 90 degrees here because the axial equatorial will still be 90. But the other one says less than 120, and that's because this lone pair here, it's actually going to force these two equatorials closer to each other. So this is not exactly 120 right here between the two equatorials. It's a little less than 120. And we don't really know the exact bond angle unless we know the exact atoms that are involved. And there's a lot more complicated, calculations involved with that. So these are the ones that can have 5 domains. There are other ones. I didn't build any of the other ones because I can kind of take this one. I can take, let's see where to go. I can take another equatorial atom off of this one, and I can replace it with a lone pair, and it's going to make the next one. This one is T-shaped because it looks like a letter T, because I've taken 2 of them are non-bonding and 3 of them are bonding. So it's still total of 5. So if I go back to the notes. Switch back over. Sorry, guys. Okay, so if I go back over here and I go down to kind of the next section, again, I still have 5 total electron domains in the first column. So my electron domain geometry, it's still trigonal bipyramidal. That's not changing. But now if I look at the second column, bonding domains is now 3 and non-bonding is 2. So now I'm going to have 2 lone pairs like this Lewis structure right here. And so this is kind of what a model would look like. And so this is kind of what it would look like in real life, or not in real life, but in a molecular model in 3D. So I can see it's making a T shape here. And then I have these 2 lone pairs that kind of sit on top. But remember, it's really like this, because if I compare it to this other one, oops, let me turn it the right way. I can see that, again, they look similar in shape. It's just that like these 2 bonds have been replaced by these 2 lone pairs. And so that's, again, going to kind of affect the angles. On this one, though, notice there's only 1 angle. It's less than 90. And that's because now there's only really these 2 angles, and they look like 90 degrees. But because of these 2 electron pairs repelling them, they're actually going to be a little less than 90. Okay. And it's kind of easy to remember. This one is T-shaped because it looks like a letter T. Okay. Oops. The last one would be if I pulled off this last one down here and I replaced it with a third lone pair. So it would look like this. Okay. So now that I replaced all the equatorial atoms with lone pairs. And so you can see it's a straight line. So this is now linear for the molecular geometry. So again, we're not changing the total electron domains. There's still 5. So technically it's still trigonal bipyramidal for the electron domain geometry, if I'm counting all of the electrons, bonding and non-bonding. But then if I look at bonding, I only have 2 bonding domains now. The non-bonding is 3 because there's 3 lone pairs. And so that makes it now linear. And anytime you have linear, that's a straight line. So just remember, to geometry, straight line, the angle is always 180 degrees exactly, because that's the farthest they can get away from each other. All right, so then the last group are the ones that can have 6 electron domains. So if you have 6 total electron domains, this electron domain geometry is called octahedral. And it's octahedral, even though it's kind of like, well, octa means 8. And so why is it octa when there's 6 electron domains? It's octahedral because, again, if I were to like fill this in and make it look like a 3-dimensional shape, like you think of in geometry classes, it would have 8 sides. So it's octahedral because it would have 8 faces. Okay. And so I can see this yellow one's my central atom. I got 1, 2, 3, 4, 5, 6. So there's 6, all 6 of them are bonds on this first one. No lone pairs, no non-bonding. And so again, the molecular geometry is going to be the same as the electron domain geometry, since there's no non-bonding electrons. Now on this one, everything is 90 degrees. So axial equatorial is 90. If I turn it this way and I do equatorial, it's still not, all of them are exactly the same on this one. They're all exactly 90. Okay. All right, if I take away one of them and replace it with a lone pair, so now I have 1 non-bonding domain, still octahedral for the electron domain geometry. What changes is that it's no longer octahedral for the molecular geometry. It is now square pyramidal. And again, because if you look either at this one I'm holding or the picture in your notes, if I were to fill it in like a 3-dimensional shape, it would look like a pyramid with a square base. So it would be a pyramid with 4 sides. Okay, 1, 2, 3, 4. So it looks like one of those pyramids. It's like over in Egypt in the desert. Okay, and so that's why it's square pyramidal. And the bond angles, they're going to be a little less than 90 because octahedral was exactly 90. So this one, because of this lone pair, they're going to repel a little bit, and they're going to be a little bit less than 90 on the bond angle. If I then take away another one, so I'm going to take away this other axial one, and I'm going to replace it with another lone pair. Okay, now this is what I have. And so these lone pairs, they're just electrons. They're not bonds taking up space. And so now it's actually square planar. Because if I turn it this way, it's just a flat square. If I connected all of these atoms, it just looks like a flat square. And so if you think of planar in geometry, means like a flat plane. It's 2-dimension. And so this one, it's just a flat square where the 4 atoms would be connected. And then you have these 2 electron domains. Now notice this one, the bond angle is back to being exactly 90. That's because these lone pairs are like exact opposite. And so the bond angles are here between these bonds. Okay, so they're exactly 90. The next one, oh, that's the last one. Okay, you can go down to where you have another one with 3 on this one and it's T-shaped again, but it kind of starts repeating. So compared to like what we did in SL, like in SL, we only had 2 or 3 or 4 bonds. And so, or 4 electron domains, I should say. So, if you had like, this one has only got 3 domains. And so this one was trigonal planar. Okay, they're all bonds. Okay, I could have something with 4 where I have something that looks like this. 4 bonds, 4 electron domains where they're all bonds is tetrahedral, like this. If I take one away and replace it with a lone pair, it's trigonal pyramidal because it looks like a pyramid with a triangular shaped base instead of a square shaped base. And then if I replace another one with a lone pair, then I end up with bent. So this is like water, and this is just the bent shape. Okay. If I have 2 electron domains, there's a lot of different ways it can look. Okay. This is carbon dioxide, so it's 2 double bonds, but it's still linear. It's a straight line. This is hydrogen cyanide, or HCN. And so this one's got a single bond and a triple bond, but again, still just 2 electron domains, 2 areas where we find electrons. There's just 3 pairs here and 1 here. whereas this one's got 2 pairs and 2 pairs, okay? But they're the same shape, okay? Because they have the same number of electron domains. When I go down on my simple, like my diatomic elements, so like here's nitrogen, N2, and it's got a triple bond. Here's oxygen, O2, it's got a double bond. Hydrogen, H2, it's just got a single bond. These are all linear. Anytime you just have 2 elements connected, it's got to be linear because there's no other way it can be because it's just 2 things connected, okay? So even though one of these is single, one's double, one's triple, they all still have just 1 electron domain here connecting the 2 atoms, okay? So continuing on to the next section, we're going to talk about sort of like how do bonds and bonding, how does this play a role sort of in the real world, okay, or, you know, in real life. And one of the ways is that it plays into the destruction of the ozone layer. And so this is kind of relating to some environmental science here. So there's 2 main types of compounds that we're going to talk about that you guys need to kind of be able to explain how this works. The first one's nitrogen monoxides, and sometimes they'll make it more generic. They'll do NO and they'll put an X here because they're like, it could be like nitrogen dioxide or trioxide. But, you know, so the X is just kind of a placeholder for the whatever subscript it might be. So this example that we're going to talk about is nitrogen monoxide. So what happens is any kind of combustion engine. So combustion engines are how cars run. They're how like trains run, buses, airplanes, and even a lot of like factories that have machinery in them. Anytime you're burning coal, oil, or gas, that's a combustion engine because you're burning some sort of hydrocarbon, some kind of compound that's got a lot of energy in it. You're burning it and you're releasing the energy in order to convert it to mechanical energy and make your engine move, okay? And so what happens is in combustion engines, really, really high temperatures are reached, okay? And what happens is when you have a combustion engine that's producing stuff at a really high temperature, there is nitrogen gas and oxygen gas that react. And when they react at a high temperature, this is the reaction they do, okay? The nitrogen and the oxygen gas react, and they actually make these things. And if you notice, they have a dot on them. Anytime you see something like that, where you have any kind of formula with a single dot, that dot is a single electron. And so that substance is called a radical. And we're going to talk more about this when we get into organic chemistry, because that we see a lot of that in organic chemistry. But radicals, or sometimes they're called free radicals. Radicals are things that have a single electron, so they're not stable, okay? Because we know from past stuff that the electrons to be stable, everybody wants to be paired up, okay? Because they always want to be paired up in an even number. So what happens is it makes this nitrogen monoxide radical, okay? And that's not very stable. So that nitrogen monoxide, when it comes in contact to something it can react with, it's going to react really quickly. And so what happens is we give off these nitrogen and oxygen gases at high temperatures. They go up into the atmosphere. The nitrogen monoxide radical is made. And then once it gets up into the ozone layer and it starts coming in contact with ozone, which ozone is O3. So this right here, this is ozone, O3. It's going to come in contact with the ozone, and it's actually going to do this like 2-step reaction, okay? So it's called a mechanism, and we're going to learn more about mechanisms when we get to topic 6, and we talk about rates of reaction and how some reactions happen in like multiple steps versus some happen in 1 step. But a mechanism is where I'm showing the individual steps that took place for a chemical reaction. Because, you know, in prior chemistry, we're just like, oh, here's the chemical equation, here's how the reaction happens. But in reality, when you kind of look behind the scenes, sometimes there's 2 or 3 steps that are happening to make that overall reaction happen. And so a mechanism is where we kind of break it down and we're showing kind of the behind the scenes details, okay? And so what happens here is there's kind of 3 steps here. The first step is to take your reactants and you make your first product. And this is called an intermediate. It's called an intermediate because, as you're going to see, it's going to be used up in the next reaction and then remade again. So anytime you produce something and then you use it in the next step in the reaction, that's called an intermediate, okay? So what happens is one of these nitrogen monoxide radicals, it starts the next step in the mechanism. It reacts with ozone in the ozone layer, So it goes into the atmosphere, it encounters some ozone molecules, and it says, hey, I can react with you. I'm going to take some of your electrons, and we're going to, change and make some new stuff. And so what happens is you end up producing nitrogen dioxide gas, and you produce just molecular oxygen, O2, oxygen gas. Okay. Then there's one more step. The last step is the nitrogen dioxide that you produce here. It goes down and it starts the last step. And what happens here is that nitrogen dioxide, it's going to encounter an oxygen radical in the air, and it's going to end up bonding or giving some electrons away. And so it's going to create more oxygen and then another nitrogen monoxide radical. So what ends up happening, the reason this is so dangerous and bad is because this NO radical right here, guess what? That's going to go and it's going to start the whole process again. It's going to do both of these steps. It's going to do it over and over and over because it's always going to end up producing another NO radical in that last step. And so that NO can then go find another ozone molecule to react with and do this same thing. And then it can go find another one. And so it just kind of keeps happening. Once it starts, it just keeps happening. And so that's why it's so dangerous, is because it happens over and over. And then we end up getting holes in the ozone layer because there's so much ozone that's been destroyed. Okay. So if I go back and I kind of look at these individual mechanism steps, I can see that the actual reaction that's happening is just ozone being destroyed. Because if I look, here's the NO radical, and then I remade it here. So it's on both sides. So it cancels out, because anything that's on both sides, it's not really part of the reaction, the overall reaction. I made NO2 and then I used NO2. So NO2 is also, it's an intermediate. It was made and then it was used up. So then if I look at what's left, I have ozone and an oxygen radical on the reactant side, and I have 2 molecules of oxygen on the product side. So this is the overall reaction that's happening, but it doesn't take place if there's none of that nitrogen available. And so that's why combustion engines that produce that nitrogen gas that goes up and makes this nitrogen monoxide radical, that's why that you hear people talk about, oh, get a hybrid car, get an electric car, or ride your bike, or don't take the bus, or they say carpool so that you're not giving off as many exhaust fumes from your car. Because every time that we're doing something like that, more of this is going up, and it's just keeping this process going and going. And so because there's been so much industrialization, we have like cars everywhere and there's factories everywhere, there's just so much now because of the advancement of technology. We're making this happen more than it should. And so that leads to things like climate change, because the ozone layer is being destroyed, ecosystems are being disrupted. It can lead to people getting increased chances of skin cancer, because if the ozone layer is not there to protect from some of the harmful UV rays, then it's going to possibly impact people and cause cancer and mutations in their cells more. So, it's kind of combining a lot of different parts of science, but the basic reason that it happens is because of these chemical structures and because of the bonding that's going on here. The other one, and this is kind of the same thing, it's just a different type of compound, but it's the same overall process that's happening, are these compounds called chlorofluorocarbons. Chlorofluorocarbons are a type of organic molecule. So we're going to see them pop back up again when we get to like organic chemistry. But chlorofluorocarbons, it's kind of like the name sounds. They're compounds that have chlorine, they have fluorine, and they have carbon in their compound. Some combination. So on the example that you have down here for your practice, they gave you CCl2F2. Okay. It could be CCl3F, or maybe CClF3. Okay. But there's going to be some combination of a carbon and some fluorine and chlorine. Okay. What happens is you start off with the same thing. I start off with a reaction that I'm going to make a radical. And so for chlorofluorocarbons, you end up with a chlorine radical. And so what happens is, let's say, I'll do the C. Let's say we have C, or sorry, I meant to do C. Let's say that we have CCl3F. Like, let's say that's the compound they give us to start with. Well, that is going to break down, and it's going to make 2 different radicals. So we're going to get up with CCl2F that has a dot because it's a radical, And then the other chlorine, it's going to be given off by itself. So it's just a chlorine radical, Cl with a single electron. And then once that happens, then this two-step process starts, okay? We take this chlorine radical that was made here, it goes here and it starts the process and it goes up in the atmosphere. It reacts with some ozone molecules. It makes some oxygen gas and it makes this chlorine monoxide radical. That chlorine monoxide radical goes down and starts the second step where it reacts with an oxygen radical. It makes more oxygen and it makes another chlorine radical. And so just like the NO radical in the first example, the chlorine radical, then it can go back and start the whole process over again. So again, it's like happening over and over because of that chlorine radical from the chlorofluorocarbon compounds, okay? And so the reason, again, these are so dangerous is because, you know, that those radicals are going to keep going back and repeating it because they keep getting regenerated is kind of the word we usually use, because they keep getting made as a product. So they keep going back and reacting with more ozone and destroying it. And so if you look though, the end equation that you end up with is exactly the same, because the chlorine radicals cancel out and these chlorine monoxide radicals cancel out. So you're left with ozone and an oxygen radical, and then 2 molecules of oxygen on the product side. So overall, these 2 equations are doing the same thing. It's just 2 different chemicals that are causing it. And so chlorofluorocarbons, they were used as refrigerants. So when they first started making like refrigerators and freezers and coolers and things that kept food and drink cooler, they used chlorofluorocarbons because they worked really well. They kept the coolers working and all that kind of stuff. They were easy to use. It wasn't until later that they figured out, oh, these chemicals are causing some dangerous harm to the atmosphere. We should probably not use them anymore. And so once they discovered that, they no longer used them, but they did use them for a long time, and it caused a lot of damage. It kind of sped things up. Oops. Okay, I don't know why it's skipping around. Okay, so this last little section has to do with the pi electrons that we talked about in part 1. And so pi electrons are the ones that are formed by double and triple bonds, okay, because they're the p orbitals where they overlap sideways. And so there are some situations, and some of you guys already sort of saw it on Tuesday when you were doing your exercise questions, and because I had people that were asking, well, these all look, the formal charges on these are the same, so how do I know which one is best? Because they look exactly the same. And the biggest example of this is the one with CO3 with a -2 charge, which is, where's it at? This one right here. So this one that was one of the examples from last time, if you look, these are actually exactly the same. The only difference is this double bond, it's like rotating where the double bond is. It's still a carbon, it's still 3 oxygens. One of the oxygens is double bonded, the other 2 are single bonded. So all we did was like we rotated it, a little bit. And so when you calculate the formal charges, they're exactly the same on all of them. One of the oxygens is one charge, the other 2 oxygens are the other formal charge, and the carbons are all the same. So in reality, there's no best structure. All of these are correct. So it's kind of like a trick question. And the reason that they're all correct is because that type of molecule actually has what we call delocalized pi electrons. So there's not, in reality, there is actually not a double bond in that molecule, okay? That double bond, which is the pi bond, it's actually delocalized. Delocalized means that it's shared by more than 2 nuclei. So it's not in between 2 atoms. It's kind of moving, it's rotating between all of the bonds in the molecule, okay? And so a lot of times, instead of drawing, well, you can draw 3 different structures like that example from last time, or we can draw what's called a hybrid structure, and we draw it like this. So if you notice, this looks really similar to the one from last time. The only difference is it has this dashed line on each bond. And what we mean, or what that shows us, is that shows us there is a pi bond here, but the pi bond is kind of rotating, it's resonating through all 3 of those bonds. Okay, and so in reality, there's not 2 single bonds and 1 double bond. There's 3 bonds that are all exactly the same, and they're like somewhere between a single and a double bond. They're like 1.5, okay, or 1 1/3, something like that. So what this means is that it just means that they're going to be stronger than a single bond, but weaker than a double bond in terms of strength. And in terms of bond length, they're going to be shorter than a single bond, but they're going to be a little longer than a double bond because they're in between. So all of their properties fall in between as well. The other compounds that you guys need to, or molecules that you guys need to know that do this, this one we're going to see again a lot more when we get to organic. It's called benzene. So benzene is a cyclical molecule, and that means that they're in a ring. And so when we draw it, it actually looks like a hexagon like this, okay? And so it's a cyclical molecule, meaning they're not in a straight line. They're in a circle. They're all connected in a circle, or it's actually a hexagon. And so, but if you notice, everything is, it's when we actually draw it out, like if I were to actually draw it, it's like every other bond, there's a double bond. So the double bonds could be here, or if I rotate them one spot, the double bonds could be here. Okay. So because it could be either version, we draw it like this with the little dashed lines. And so a lot of times benzene gets its own special thing. It looks like this. They draw the hexagon, but instead of drawing dashed lines or the bonds alternating, they draw a circle in the middle. So if you ever see a structure drawn like this in like movies or TV shows, that's benzene. It's a benzene ring. And so it's a really common thing you see in organic chemistry. And so you just kind of know to start recognizing that, because we're going to see it pop up a lot more. And it has a lot of special properties and things when we get to organic chemistry that we're going to talk about more in detail. The other molecules that you guys should sort of recognize that they do this, they have the resonance structures because they have these delocalized pi bonds, are the ethanoate ion, which ethanoate is the same, it's another word for acetate. So acetate is the non-organic name, ethanoate is what it's called in organic chemistry, but they're the same thing, okay? The nitrate ion, and then the ozone, the molecule we just talked about, okay? So the ozone molecule, it's stronger than a single bond, but not as strong as a double bond. And so that's why it's able to be destroyed by those other things, because the bond, it's like in between a single and a double. It's not as strong as oxygen like the double bond. I kind of already mentioned this bond length and strength stuff. So they're in between single and double. So usually we say that the bond order is 1.5. If you have a single bond, the bond order is 1. If you have a double bond, the bond order is 2. If you have a triple bond, the bond order is 3. So when you have something like this that has those delocalized pi electrons, it's in between single and double. So we usually say that the bond order is 1.5. And that means that the strength and the length are going to be somewhere between a single and double bond. Okay. That is it for today. We'll get into 14.2, which deals with hybridization next week.